Okay, so here we go. And hopefully at this point you've had your aha moment. I'm guessing a little bit that we're already up to this point. I'm not sure if we're going to get this far in one day, but even if we didn't, it's okay. So I don't really know how this happened, but if you look at the middle of page 10, something seems to have disappeared. Maybe I printed the wrong file for you, but I want you to write something in here, right over here, before we get to ideal gases versus real gases, and that's Avogadro's hypothesis. Yes, this guy again. I know, but Avogadro's hypothesis, and I'm just going to give that to you, what that hypothesis is, and this is really what he's so well known for. It's not for coming up with 6.02 times 10 to the 23rd. That number was named for him. It wasn't actually him that came up with it. Obviously, that'd be really amazing if he did that in the 17th or 16th century. So here's what his great hypothesis was. As it turns out, he was right, and this is what the big deal was. He said that if you have equal volumes of different gases at the same temperature and pressure, the two samples, I would say equal volumes of, equal volumes of, have the same number of moles, which is really, in a way, saying these have the same number of molecules, because if they have the same number of moles, then they have the same number of molecules. Now, that is a really mind-blowing thing, because, if you have a balloon that's full of, let's say, oxygen, and another balloon that's full of hydrogen, then if they have the same volume, they weigh very different. Oxygen, if you have a mole, let's say, of each, oxygen weighs, 16 plus 16, that's 32 grams, and hydrogen only weighs 1 plus 1, 2 grams. So that's a big difference, and he made this hypothesis that while they weigh differently, they have the same number of molecules in them. And in fact, that was the beginning of understanding atomic mass, because he could come up with atomic mass this way. And now, that's all lovely, and that's a lovely story, and you've just written something down, and that's nice. But really the best way to remember it is to use a song. So I want you to go back into Chrome. Oh, it doesn't be Chrome, but I want you to go to YouTube. I don't care what web browser you use. Go into YouTube, and then you can take a look at, I want you to look up Avogadro's hypothesis song and use OFFUTT. Michael Ofoot is the guy who wrote it. The same guy from the Mole song, so you'll be very happy to hear it. And there it is. Go play that link right there. First one up, Amadeo Avogadro, Michael Ofoot, and I want you to listen to that. And part of your homework for tomorrow is that you have to be able to come in and sing the chorus of that song. So if you can't sing the chorus of the song, that means you didn't do your homework. So that's going to be part of me checking your homework tomorrow. Now you can go back to page 10 after you're done watching that, and we can talk a little bit about ideal gases versus real gases. See, because as it says here in the notes, all of our gas laws so far have been based on ideal gases. We made some initial assumptions back on, you can flip back to page 2, you can pause this for a second if you need to and refresh your memory. Kinetic molecular theory tells us about, the assumptions that we made to make our math really easy. P1 V1 equals P2 V2, Boyle's law. That wouldn't work if we were making all the adjustments for real gases. But the truth is that we don't live in an ideal world for a lot of reasons. And, we have to think about when we can use our assumptions for ideal versus real gases. And in order to think about that, you need to understand when kinetic molecular theory begins to break down. So, what is the biggest deal in kinetic molecular theory? If you look at all three things, you'll see that the biggest deal is that there is no attraction, or we should say, assume that there is no attraction between molecules. Molecules or molecule particles also have no volume. That's an assumption. Of course, we know that's not completely true, but that's the assumption. Are these things true? Well, why would I ask if they were true? It depends. Sometimes they're more true than others, but in general, you can say, no, they're not true. Okay? Because if gases were always ideal and they didn't have any attractions, Would you ever have liquids or solids where there are attractions between them? Boy, I wish you could see my hands, but I'm not going to give you the webcam, sorry. But anyway, apparently I have an audience back here. But they wouldn't
Hello.
The webcam's not on, guys.
Wait, and if you're wondering about that, all that black stuff, that's all mine.
Okay.
And mine.
Well, not really.
Okay.
Billy.
So
Okay,
gases.
bye.
So gases. Liquids or solids wouldn't ever exist if the molecules didn't attract each other. So we need to talk about how they do differ from ideal gases.
Hello again.
Serious? Oh, wait.
I'm going to pause this recording here. Oh, maybe I can't. I don't know. All right. Well, how do real gases differ from ideal gases? They differ from ideal gases in two ways. One way is that they have intermolecular attraction.
Crunchy, 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 crunchy.
She's eating nacho chips. It's very exciting.
Let's go.
All right. I think we're going to have to stop this video for a second and settle the troops down here.